Today is 31st of March 2025. Pinned OS questions during the class. Our first question was a difference between preventing the same PID and preventing different process entering simultaneously, and both has common about in the sense of synchronization problem. For the first one, we should there will be kernel variable, next a variable PID, then we should mutually exclude it. We can use synchronization tool, add synchronization tool to solve problem. For the preventing different process entering critical section simultaneously, there are solutions such as Peterson's, semaphore, mutex, so on. Peterson's are more theoretical. If not atomic, it's not working, and it has condition of bounded weighting. For mutex and semaphore, they don't have conditions. Mutex and semaphore doesn't support bounded weighting, and for fifth remaining time first. If you see the picture of the how shortest remaining time first, it's the first pre-imperative version of SJF, which means while it is processed in CPU, it doesn't exist in Cray. So if you calculate the average time, then for P1, it will wait from the birth time is 8 minutes, and it exists in here to here. So it should wait for 10 minus 1, 9 minutes. And for P2, when it arrives, it just burst directly. So it's just 1 minus 1. But in graph, it is from 1 to 5. P4, it will take from 17 to 2. No, it's P3, P. So last one is from 5 minus 3. Oh. For slide 5.40, version 1. Load balancing and push migration and pull migration. And for the sentence OS deprived resource, acquiring critical section by disabling interrupt means if interrupt didn't perform, then context switching will not happen. So OS deprived resource or processed by interrupt. So if you disable interrupt, then other process, you cannot do context switching. And for round robin, it is if there's n process, then you give same amount of time. So fixed amount of time is given to every process. You can use it with time sharing. And for priority scheduling, first there is priority, so you can do first a process, the process which has high priority, and after then you use round robin manner. And for the real-time process and interactive process, batch process and system process differences, real-time process has a deadline, and interactive process has a such as shell program that usually need input, and system processes are usual process to work over properly. So real-time process and system process has high priority, and process has the lowest priority because we don't know how much time is needed to finish interactive process. So it is we do the batch process after other things are finished. Batch process could be interrupted also. And in this chapter, which is CPU scheduling, process is defined by arrival time and birth time. So in this slide, what it shows is P1 is RR with round robin with time quantum 8, which means when you pass this, it has possibility to go to CPU or go to another queue. Once you go to CPU, then it will use burst time of 8. Q0 or Q0s. So which means if there's process that needs burst time 10, then if it passes through it and goes to CPU, then it has remaining burst time of 2, so it will go to second queue. And for the PCS and SCS difference, PCS is per process and SCS is per every thread to compete to use CPU. So the important thing is only one thread can get in, so we cannot say it is they are sharing it. They are competing each other. For this part, there can be various type of multiprocess. For multi-core CPUs, only one CPU has multiple cores. And for multi-threaded cores, it is core supported multi-thread. For NUMA system is non-uniform memory access system, which is access time on memory is different by depending on which core use memory. And for heterogeneous multiprocessing, CPU has one process handle for scheduling for a system task. Each of CPU has one process. And this is how multi-threaded multi-core works. Each core has more than one hardware thread. You can think of it as hyper-threading. So in operating system view, even there is four core, but because each of it has two hardware thread. So in operating system view, they have 8 thread. So they have 8 CPUs. So when one thread is doing M, the other can do C. While CPU doing memory-related instruction, another thread can take core and run it. And for 2 CPUs or 2 different core access to one semaphore, it may cause race condition.